So moving on to the second part of lesson 3 in chapter 6, we're going to keep talking about vectors. And first thing that we need to kind of remember is what we talked about with a unit vector. And a unit vector is just a vector that has a magnitude or a length of 1, right? So when we look at what are called the standard unit vectors, okay, the standard unit vectors are used or are represented by a bold I, okay? And we got to make sure the I is bold when we do this unit vector, because regular I, it represents imaginary numbers square root of -1. So this isn't imaginary number. This is a unit vector I. And you'll use this unit vector a lot when working with vectors. It's just the vector 1, 0. So essentially it's a vector where you go right 1 and up nothing, right? Just straight out across the x-axis 1 unit. And then the other one is a bold J. So we'll use these two a lot when talking about unit vectors. And it's if you go over 0 and up 1. So those vectors are your standard unit vectors. And the cool thing about those is that we can use them to represent any vector. So if I have some random vector, vector v, and its value is, v1, v2. Okay, well, we can write that vector using the standard unit vectors by just taking v1. So we can say that vector v equals v1 times I, the I vector, plus v2 times the j vector. Okay, and you'll see this used a lot, and we call that a linear combination of unit vectors, or you could maybe call it unit vector form. So this first form that we're used to seeing already is component form, and then this would be like unit vector form, or maybe sometimes you could call it a component of linear, or a combination of linear vectors. I like to call it unit vector form. So you got component form and unit vector form. So it's just another form to write your vector in that you'll see a lot. All right, so let's look at example 1. It says let u be the vector with initial point 2, -5, and terminal point -1, 3. Write u as a linear combination of the standard unit vectors. So basically write it in unit vector form as opposed to in component form. So first let's figure out what it is in component form. So we got the 2 points it starts at and stops at. So we remember that we can find the vector by just taking the x's and subtracting them, right? So we do the terminal point, -1 minus the initial point. And the same thing with the y values, 3 minus -5. And that gives us our vector u. -1 minus 2 is -3. And then 3 minus -5 is going to be +8. So there's the vector in component form that we're used to seeing. So now all we've got to do is change it to unit vector form. So we're just going to take the x value and we're going to say, all right, u is going to be -3, and we put the bold I with it, and then we add 8 and put the bold j with it. Okay, because if you take -3 and multiply it by the unit vector, right? So this is just kind of showing you why this is true. Take -3 and multiply it by the unit vector I, right? That's going to give me -3, 0, and we add that to 8 times the unit vector j, which is 0, 1. That's going to give me 0, 8. Then when we add those, it'll give us -3 and 8. When we add -3 and 0, we get -3 and 0 and 8, we get 8. So you can see why doing -3 times I and adding it to 8 times j will give us that original component form that we had for the unit vector. Okay, so this right here is our answer. All right, and it's showing you down there why that works, okay? Because when you actually plug in what I is, remember I and j, I is 1, 0 and j is 0, 1. So when we plug those in for I and j right there where our answer is, and multiply and add it, we can see that it goes back and gives us what we have. So just kind of checking our work right there. You don't have to do that, but just a way to know why it's working that way. All right, so you guys try this one, then we'll go over it. So we subtract the x's in the terminal point. Remember, you got to do terminal point minus the initial point. So 4 minus -3 gives us 7, and 5 minus 1 gives us 4. So our unit vector form for the vector u is 7i plus 4j. Okay, so moving on to vector operations whenever we are in unit vector form. It's pretty simple. So right here we got u and we got the vector v, and they're written in unit vector form, and we want to find 2u minus 3v. So we're going to do 2 times negative 3i plus 8j minus 3 times 2i minus j. Okay, you just treat it like you would any like terms, anything you would do for variables. 2 times negative 3 is negative 6i, 2 times 8 is 16j. And you've got minus 3 times 2i, so that's minus 6i, and minus 3 times minus j is plus 3j. Now you just combine it like terms. Negative 6i is negative 12i, 16j and 3j is 19j. Okay, so that would be your answer. Now, if they wanted you to write your answer in component form, then you would just do negative 12, 19 if they asked for what's the answer in component form. All right, so there's your answer for that one, and go ahead and try the one down here, and then we'll go over it and see how you do. All right, so right here you can see the work. 4 times the u vector gives us 8i minus 20j, and then negative v is plus 2i minus 3j. Once you multiply by the negative, then you just combine like terms. 10i minus 23j is your answer in unit vector form, or if you want to write it in component form, you write 10 negative 23 inside your diagonal brackets. I'm not really sure what the terms for those are. I have to look that one up. All right, so let's move on and talk about direction angles. So essentially what a direction angle is let's look at this on the unit circle. Okay, so let's say on this unit circle right here, I draw a vector out here somewhere, and it stops at some xy point, right? So it stops at some xy point. Well, it makes an angle, obviously, with the x-axis down here, right, called theta. So what we're talking about with direction angles is that angle. What is that angle in there that is made by that vector? So we remember, though, that on a unit circle, x, right, is cosine of theta, and y is, of course, sine of theta. So what we get when we look for the vector, okay, the vector is, of course, from 0, 0 to xy. So our vector, whatever that vector v is, we called it v. V is going to equal the cosine of theta, because that's x, times the unit vector, plus the sine of theta, times the j vector. All right? So, because those are x and y, right? Cosine is x coordinate, sine is the y coordinate. So just like, we did over here on these, we take our x coordinate and y coordinate and multiply them by I and j, right? So you got your x coordinate negative 3 and your y coordinate 8, multiplying by I and j to get the unit vector. Same thing we're doing right here. We're just saying, all right, well, with using trig, the x coordinate is cosine and the y coordinate sine. So we'll say cosine of theta times I and sine theta times j will be the unit vector right there. So now another thing to extend, let's say we extend this vector out past the unit circle. So its magnitude now is not 1, it's not a unit vector, it's just any other vector. Okay, then the formula that we end up getting right there is we want to take the magnitude of that vector, whatever it is, however long we go, and whatever its length ends up being, and multiply it by each of those two parts. So we would say the magnitude of v times the cosine of theta I, okay, because we're going to make the vector longer. So now it's not the x coordinates and y coordinates are going to be multiplied by the magnitude plus the magnitude of v times sine of theta j. All right, so that's something that we're going to use on some of these problems here coming up to find the direction angle, right, to actually figure out what is that angle that the vector makes. Okay, so let's start simple first. We want to find the directional angle of each vector. So we're told that u is the vector 3i plus 3j. Now there's a little trick to doing this. All you do is you take the number that's in front of j and you put it over the number in front of I. So in this situation it would be 3 over 3. And we say that that has to equal the tangent of theta, of whatever our angle is. And the reason why is because if we make a triangle out of this, well, this is the y coordinate, this is the x coordinate. So if we know the y and x coordinates, then the tangent of theta is y over x, opposite over the adjacent, right? So we're just using our knowledge of trig, tangents, opposite over adjacent. We know the opposite is 3, because this, remember, is like our x and y right here, or our sine theta and cosine theta. So tangent theta is going to equal 3 over 3. And now you do the arc tangent on the calculator. Well, that's tangent of theta equals 1. And we can know when tangent of theta is going to equal 1 in that first quadrant, okay? Because we know 3, 3 is over here in the first quadrant. And we know tangent theta is going to be 1 at 45 degrees. So theta is going to equal 45 degrees. We know that just in the unit circle. Now, sometimes they're not going to be that clean. It's not going to be a value like 1 that is on the unit circle. And so then you'll have to use the arc tangent button on your calculator to figure out what value that's going to be. So let's look at B part right here. So B, we've got the y value -4, which we're going to say tangent theta equals -4 over the x value 3. Okay, so this is an example of one that is not on the unit circle, right? So whenever it's not on the unit circle, you got to use the arc tangent feature on the calculator. So it's second tangent of -4 over 3. Of course, you want to make sure you're in degrees, so you get your answer as a degree measure. And we get theta is -53.13. All right. So then from that point, you want to try to figure out where is that angle going to be. And we want to actually figure out a positive angle for that, not a negative angle. So if that's negative, well, the direction angle of that vector, so -53, is going to bring it down here, right? -53 degrees. So what's the actual angle, the positive angle? So if we add 360 to that to get the positive value of this angle, okay, that's what we want to find for theta, not a negative angle. So when we add 360, we get 306.87 degrees. All right, so now we know this vector right here, V, right, that was our V vector. It comes down to the point 3, -4, somewhere down here. We go over 3 and down -4, somewhere down here. Whatever that point would be. Obviously, this is a unit circle, so it would be really way out here somewhere, back out, 3, way down here somewhere, -4. But you get the idea that wherever that point is, that vector that goes to that point is going to make this big angle, this 306.87 degree angle. All right, so you're just going to plug them in, do tangent theta equals, and then each of the component parts. Make sure you do the number in front of J over the number in front of I. And once you get your answer, of course, you want to figure out what would the positive angle be between 0 and 360 degrees that would get you to that vector. All right. So try these down here. Give these a try, and I'll go over how to do them. All right. So let's actually look at the second one right here, B first, the V vector, because it's a little bit simpler. So we do tangent theta equals, and we do 15 over 12. Type that in the calculator, hit second tangent, 15 over 12, and you get 51.34. Now notice that this one is in the first quadrant, right? So you've got your vector goes to 12, 15. So that theta that you found is in the first quadrant, right? So that answer we get is the answer we're going to use, 51.34. Now the first one's a little bit different. So you're still going to set up the same way. Tangent theta equals +5 over -2. Do second tangent, do the arc tangent, and get -68.20. Okay, so you got to realize that is -68. So that's coming down here, right? So this is -68.20. What we want to figure out is what is the angle up here that we're going to get to, right? Because we got to get to -2.5. So a couple ways you could do that is just find the reference angle for this. So if it's -68 below, then the reference angle up here would be 68.20 above. Okay, and then of course, if the reference angle is 68.20 there, then that's going to be the same thing over here, right? Because remember, reference angles is how far is the line from the x-axis, right? So it's going to be, this line right here is going to be 68.2 degrees from the x-axis. So now what we got to do is subtract 180, because all the way from the positive x-axis around to the negative x-axis is 180 degrees. So you just do 180 minus the 68.2. And so our answer is 111.80 degrees when we round it off. So that angle from to get to that vector is 111.8 degrees. So on a lot of these, when they're in other quadrants, you need to find the reference angle. So if it's negative 68 degrees is your answer, well, the reference angle for that's just 68 degrees because that's 68 from the x-axis. And then look in that other quadrant and figure out what's the angle that would have to be in order to be that far from the x-axis. Now, if it comes down to the bottom quadrant, right, and this is your vector right here, and let's say the reference angle was 40 degrees, all right, so you type in the second your arc tangent or something, and you get 40 degrees. So that means that this vector has to be 40 degrees from the x-axis. So that would be 40 right here. So you'd say, okay, well, I got 180 plus the 40 more, so my answer will be 220 degrees. So just take whatever you get when you do arc tangent, make that your reference angle, and then in that quadrant, figure out how far that vector is, or use that reference angle to know that's how far that vector is from the x-axis, and just use that to calculate what the angle is to get to the vector. All right, let's roll on and look at some real-life problems on how to do this. So you want to find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizontal. All right, so let's pretend we've got us an airplane. I'll draw a little airplane here. Excuse the terrible drawing. And we got windows and all that stuff, tail fin. All right, so we got an airplane, and it's going to be descending, right? So it says that it's descending at an angle of 30 degrees below the horizontal. So if we draw a horizontal out here, I should have tried drawing it coming down, but we got it coming down at an angle of 30 degrees. All right, and this is just the picture that I was given. If you thought about it going the other direction, down 30 degrees, that's fine. You can still calculate it going the other direction, but this is just what they drew in the picture I saw. So it says it's coming down at 100 miles per hour. So this vector path that it's on, okay, remember vectors measure magnitude or length and direction, right? So there's the direction it's on, and it's going, its magnitude or its length is 100 because we're going 100 miles per hour. So what you're going to do is use the formula that we wrote down on this last slide, this formula right here. Okay, we're going to use that to figure out what is the vector that this plane is on. What is the actual component form of that vector? So vector v, okay, it's going to be the magnitude of v times the cosine of theta I plus the magnitude of v times the sine of theta j. Okay, and we already know the magnitude of v, the magnitude of the vector is 100. So we'll say 100. All right, and then we got to do the cosine of theta. Okay, so what is theta? Well, if we've got the positive x-axis right here, then this angle is really going to be coming around 180 plus 30 more. So the angle we're going to use is actually 210 degrees for theta. And we got the I plus magnitude of V, again, it's 100, times the sine of 210 degrees J. All right, so now we just got to use our knowledge of the unit circle. So we got 100 times the cosine of 210. So thinking of our unit circle, 210 degrees over here is, cosine is going to be a negative value in this quadrant. So we got negative, and 210, that reference angle is 30 degrees. So we're thinking, what's the cosine of 30 degrees? Cosine of 30 degrees is the square root of 3 over 2. So we got that times I plus 100. And the sine of 210, Of course, in that quadrant, sine is also negative, so it's negative 1/2 j, right? Because sine of 30 degrees is 1/2. All right, now you just got to multiply. So our vector is going to be negative 50 square root of 3, because 100 over 2 is just going to give us 50. I minus 100 times negative 1/2 is 50 j. Okay, so there's our answer in unit vector form. So if we want to write it in component form, we would just do negative 50 square root of 3, negative 50. That would be the vector that comes down, going in that direction. Now, if you did it, if you did it with the plane going towards the right, going down at a 30-degree angle, okay, you're going to get essentially the same values, but they would just be, you would have positive 50 square root of 3, negative 50. All right, so that just tells you a different direction that the plane would be going in. So this vector accounts for the direction, and it also accounts for the magnitude that the plane is traveling, the speed that it's traveling at. And you can check and make sure that this vector has a magnitude of 100 if you want, by plugging it into, remember how we do the distance formula, basically it's negative 50 square root of 3 squared, and then you add negative 50 squared and take the square root of them. You can do that and double check to make sure that you have a magnitude of 100, but that will work out to give you 100. So let's let you guys try this next one. Again, use that formula I wrote up there in black and figure out the answer to this problem here. So on the U-try, you might have gotten a little tricked up just because 40 degrees isn't on the unit circle. So again, if it's not on the unit circle, we have to resort to just typing in the calculator and getting a decimal and approximating. Okay, there's no way we're going to get an exact answer without having some unit circle number to use. So you just got to plug into the formula. Do 70 times cosine of 40 I plus 70 times sine of 40 j. So whenever you do 70 times cosine 40, you get 53.62 I, and then 70 times sine 40 gives you 45.00 j. And they said find the vertical and horizontal components of the velocity. So the vertical component is this one, remember, because j is the unit vector going up, and I is the unit vector going out, right? So 53.62 is our horizontal component. So what this means is that that ball, while it's traveling, along this path, whatever path it's on, it's traveling at 50. It's going, horizontal. If we just measured the speed, it's traveling horizontally, not the speed, its overall speed through the air, but the speed it's going along the ground. It's going 53.62 feet per second along the ground, and it's traveling 45 feet per second upward. Okay, so that's what those mean. And of course, that's going to change as it loses its momentum, but that's the initial vertical and horizontal velocities of the ball. All right. So let me know if you have any questions on any of this stuff, and you can go ahead and try these practice problems, and let me know if you need any help.